So, thank you for the invitation to join this symposium, which was actually a very interesting challenge because I didn't quite realize when I agreed that we would just had about a month to actually download, process, organize, and analyze the data. So this is a bit hot off the press, so to speak. Let's just give a little background on what was our idea, and that's basically we tried to predict phenotypes from resting state data, and then we try to extend that to movie data. So the standard approach here is that you have a brain parcellation or an atlas, then you extract the individual connectomes from that, submit that to a statistical learning procedure, and then evaluate whether you can actually predict the correct phenotype or not. Now, this has been used a lot. We're seeing a lot of examples also here on that conference, but there are a few big positives about it. It's suitable for large-scale application. It provides an unbiased, data-driven approach, and we can make some inference on relevant connections. However, there are also some downsides to it, and the biggest downside really is that the number of features in this kind of approach is usually horrendously larger than the number of examples that you have. If you work with like a 400, 500 region parcellation, maybe once the healthy brain network gets complete, we can work with that. But with the current sample sizes, it's fairly hopeless. Also, it ignores knowledge about the brain, and it's difficult to interpret. So one of the ideas that we had that I already talked about yesterday, so I'm going to do that quite fast, is to use robust knowledge on brain organization as prior information. How do we get this kind of robust knowledge? Well, we have a huge literature on task-based neuroimaging. There are like 30,000, 40,000 studies where people use task-based paradigm to scan all sorts of people. And the interesting thing is now that we have a very heterogeneous, relatively unreliable literature, but what we can do is use quantitative coordinate-based meta-analysis to find those regions in the brain that are actually robustly activated. So if you want to ask which are the regions that across hundreds of experiments, thousands of subjects, really robustly get over and over activated when people do working memory experiments, that's what you can do with techniques like activation likelihood estimation. So now once you have that, you can use the peaks that you get from that and define these as nodes of your network. So in this example, you have hundreds of studies, they activate all over the brain, you summarize that, you get your significant meta-analysis result, and then you end up with this robust a priori, and that's important. This is done before we actually have any of the data collected, working memory network. And then we can use this and then go to the new individual data and extract individual connectomes from this particular network. What we've shown here, that's a study on predicting behavioral phenotypes, in this case neo-FFI scores, is that this actually outperforms whole brain prediction accuracy, and it actually outperforms it in some cases quite dramatically. And the reason really is what I said earlier, the fact that you have a much better feature to example ratio. Now, can we also use that in the context of naturalistic viewing? So what we have is two conditions. One is rest, and the other one is the movie Despicable Me. And what we looked at here, for the interest of time, because we only had a few weeks, is just three networks. It's the social affective default mode network, reward network, and cognitive action control. So for each of these networks, for each of the 100+ kits that we looked at, we can extract the resting state network connectome. It's not the whole brain connectome, it's the resting state network connectome. Obviously represent that as this kind of matrix. And what you can already see is that there is quite some similarity between the resting connectome and the movie connectome, but they're not identical. And this is actually the interesting thing. Because now we move on and adjust it for age and gender, do a relevance vector regression to see if we can predict behavioral phenotypes using repeated tenfold cross-validation in new unseen kids. And here I show you the first results. So this is from the resting state data, And we see that the performance in the Wechsler Individual Achievement Test, or cognitive test, can not be predicted by the default mode network. It can be predicted quite well from the reward network and the cognitive network. And the same is also true when we look at the movie Despicable Me. So in this case, what we see is that basically movie and rest give us very similar out-of-sample predictions of cognitive scores. Now, in some way, that can be expected. Despicable Me is not something that is particularly cognitively challenging. Rather, the movie is based, well, depends on your point of view, but it's rather more geared towards tickling, let's say, social, affective kind of impressions. So what happens if we look at something like the affective reactivity index? Well, in this case, we see that it's not predicted by the cognitive network, not predicted by the reward network, but predicted by the social affective default network at rest. And this fits well with the great literature on the relationship between the default mode connectivity, and social cognition. Interesting now, though, if we look at the movie data, where we see all of a sudden there's a very strong predictive power of the reward network rather than the default mode network. So it kind of seems that there are two fundamentally different processes that both, however, allow quite well to predict socio-affective phenotypes. And in fact, just in a nutshell, the idea is that during rest, the default mode network is fairly self-reflexive. So it's a lot of memory, a lot of thinking about myself and others. So when you're at rest, if you don't have this external stimulus, then basically your default mode network, your psychological baseline of the brain, is about thinking about yourself and others. However, if you are driven by this kind of task, then all of a sudden, the default network is not particularly involved anymore because you don't need to generate stimulus now endogenously. You have this exogenous stimulus, and now other cognitive networks can take over. We also looked at the social aptitude set, and quite surprisingly, we found somewhat of a similar pattern. So again, socio-affective reward was very good in predicting the phenotypes when you're watching a movie. But what happened to the default network? Well, it seems the default mode network as a whole was not involved. But actually, if you look at the more specific theory of mind-related regions, then you actually do see that prediction. Now, what to make out of this very initial data? First of all, I think this new data on the movie watching underlines how good meta-analyses are to consolidate data into networks and how interesting patterns emerge from that. So it really seems that we have a lot of differentiations and that basically go in this kind of triangle. I'm speeding up. So basically what I would propose is that we kind of have to measure, scan, probe, try and error in the end, this kind of golden triangle. When you have the right network and the right movie, you're going to strongly be driving the right things, which allows you to predict the phenotype very well. This has dramatic implications, particularly when we think about development and in particular clinical applications. But the big challenge is we need to find out which networks and which movies together really give you this high predictive accuracy to predict new phenotypes. With that, I would like to close and really thank those 4 people that in the shortest amount of time made a lot of things possible. Thanks a lot.